You have 6'4" and 6'5" from me. This, you should have received an email this morning. This is the rest of this week. Our exam is here, 3:30 to 5:30 on Wednesday in this room. These are all of my office hours between now and then. What questions do you have for me regarding the exam? Yes, Chris.
You just walk through like some application problems.
Like anything in particular?
Maybe some class,
So the work and stuff like that? Okay. There's one on the review sheet, and then there's one in the section in the. Is there anything in particular you were looking after? I've got things like this. So why don't we take a look at our leaky bucket? Problem number 19 talks about a 10-kilogram bucket lifted from the ground to a height of 12 meters at a constant speed with a rope that weighs 0.8 kilograms per meter. Initially, the bucket contains 36 kilograms of water. but the water leaks at a constant rate and finishes draining as the bucket reaches the 12-meter level. How much work is done? Okay, this is a non-trivial setup, but let's try and figure out what's going on. So I've got this bucket full of water. The bucket weighs 10 kilograms. And at the bottom of the well, or wherever we're coming out of, from the ground, it says, it contains 36 kilograms of water. By the time it gets up here, there's no water left. And it leaks at a constant rate. It also tells me that the rope is 0.8 kilograms per meter. And that we're hauling it 12 meters. So far, so good? Okay. I really need to think of this, in my opinion, in several different pieces. I'm going to move the bucket, that 10 kilograms, from the bottom to the top. Each piece of the rope may travel a different distance, right? We did a rope hanging the other day, right? The 100 meters worth of rope that we were pulling up, 100 feet. I think we did that by a feet. So I need to chop up the rope to figure out how much each bit moves. And then I need to figure out the water. The water drips out at a constant rate, and there's no water by the time we reach the top. If I'm going to do work, work is force times distance. And in our case, because we're dealing with weight and gravity, my force is going to be mass times gravity. So I'm going to put this together in 3 separate pieces. Let's deal with the bucket. Bucket goes 12 meters. Doesn't change the entire thing, right? Just the bucket itself. It's going to go the whole 12 meters. So for the bucket, the force is mass times gravity. And I'm going to go the entire 12 meters. Now I could actually do this just as straight multiplication, right? Because this is a constant. Let me use a dot for multiplication instead of this little time symbol. So that's going to be 144 times 9.8. Somebody grab a calculator, tell me what that is. Say again? That's the 12 times the 9.8, right? But now I'm gonna multiply by another 12. 1,411.2. And that's in joules. Because we're in metric here. Kilograms, meters squared per second squared. Let's think about the rope. I'm going to think about the rope the way we thought of the rope in the previous problem. I'm going to build the Riemann sum. Go back to my picture. How far does this bit of rope need to move? It's not going anywhere, right? So we'll call that x equals 0. This bit of rope needs to move all 12 meters. But this bit of rope right here, this little slice of the rope, how far does it have to move? However far it is from the top, right? Because we're going up. So let's give that some x between 0 and 12. So that's the distance part. The force is mass times gravity. We know the little slice of rope is 0.8 kilograms per meter. So if I know how thick this little slice is, oh, but that's just a little change in x, isn't it? So kilograms per meter times meters is kilograms. So I have 0.8 times delta x, that's the mass of the rope, times 9.8 for the gravity, times x for the distance, going from 0 to 12. Oh, okay. 9.8 times 0.8. There's my interval. That tells me how many joules it takes to lift the rope. And again, I don't know this number, but it's going to be 78.4 times 12 squared over 2, right? Because that's an x, becomes x squared over 2. What's that number? Oh, okay. I wrote down something incorrect. 9.8 times 0.8 is 7.84, not 78.4. What number did you get again, Chris? So I got 7.84, 12 squared over 2. What's 12 squared is 144. 144 divided by 2 is 72. 7 times 72. This should be around 500-ish. That's the number I got as well. Now, why did I say that I think this should be 500-ish? The bucket weighs 10 kilograms. And we're hoisting it the entire 12 meters. How much does the whole rope weigh? The information I need to know the weight of the rope is right there. Why? The bucket is 10 kilograms. How much does the rope weigh? The rope weighs 0.8 kilograms per meter. How long is the rope? 0.8 times 12 is 9.6, just under 10 kilograms. The rope weighs almost the same amount as the bucket, a little bit less, right? But we're not holding the entire rope up from the whole bottom, because part of it's already at the top, right? So it should take about half, maybe a little less. The bucket took 1,400. So the rope should take less than 700. 560. Now I need to think about the water. The water goes the entire 12 meters, but it changes because the bucket leaks. I have 36 kilograms of water at the bottom. I have no water at the top. I need to figure out how much the water is leaking out, so I know the mass at any given point in time, right? So let's think about this. The mass of water goes from 36 to 0 at a constant rate. But I don't know how long it takes. There's nothing about time in this problem, is there? But I can work out how much water is leaked per meter of lift, right? The leak is 3 kilograms of water for every meter I travel. Does that make sense? We used per meter of travel right here, didn't we? If the bucket is going from here to here, that's an X difference. Bucket goes from here to here, that's an X difference. Oh, there's my mass. In terms of X, mass times gravity is force, force over distance. I can take the 9.8 out, worry about it later. 36x minus 3 over 2x squared from 0 to 12. Now, this should be more than the bucket. Why? Say again?
Times 9.8.
But I had the 9.8 with the bucket. But why do I know still that this should give me a larger amount of work than the bucket did? Same X value, 0 to 12. I took the bucket from 0 to 12, didn't I? On average, the water is heavier. I started at 36, I ended at 0. My average is 18. The bucket is only 10. On average, there's more water than there is buckets. Even though none of the water made it to the top, there's more water weight to move. More force needed to move more weight. So 36 times 12, 3 over 2 times 144, then multiply that whole answer by 9.8. What do you get? And now you add up all three numbers to get the total amount of work done in this whole system. Ta-da! So 4,093 joules. Let's see. That is enough to keep a 100-watt light bulb burning for 40 minutes. No, 40 seconds. So just to haul this up, the power used to turn on a light bulb, 100-watt light bulb, for 40 seconds. Not trivial. A watt is a joule per second. 4,000 joules means 4,000 seconds, but it was a 100-watt light. You use a modern LED bulb, modern LED bulbs are 13 watts instead of 100 watts for the same brightness. So it would last a lot longer, wouldn't it? And that's my definition of energy efficiency. If the water wasn't leaking, I wouldn't need this term. If the water went up the whole way, I could just take the 36 and the 12 and add it together. The rope, on the other hand, doesn't go the whole way, so it's the one that has to be adjusted. I think the problem in the homework was about a rocket ship, model rocket. Just for the record, I want to prove to you that this is not a crazy idea. This water bottle of mine holds 750 milliliters of water. That weighs 750 grams. The metal bottle itself weighs 450 grams. This is your model rocket in problem 18. It's this big. less fuel. More questions, better? Yes, ma'am.
Can you go over the play?
L'Hopital, my buddy L'Hopital. Okay. L'Hopital's rule works in one and only one kind of indeterminate form, a fraction. If I do a limit and I get it 0 over 0, or I get infinity over infinity, doesn't matter what the signs are. One could be positive, one could be negative, they both could be positive, they both could be negative on the infinities. Then the limit as x approaches a of f of x over g of x is the same as the limit as x approaches a of f prime of x over g prime of x. So I can replace a function with its derivative. Now I may have to do a little rewriting, some algebra, some rearranging of terms to get the expression I'm working with to look like f of x over g of x. If it's multiplication, maybe I need to move something to the bottom and flip it over. If it's subtraction, maybe I need to multiply by the conjugate to get squares over. So there's all sorts of algebra that might need to be done. If it's an ugly power, I need an ln to get the power out. All those sorts of algebra tricks to make it look like an infinity over infinity or a 0 over a 0. That's the indeterminate I am after. So when I start looking at limits, I see something like this. And right now I'm in trouble because this is not division. Except it kind of is, because there's a negative power involved there. How can I move a negative power and make it not negative? So I'm going to write this with 1 over e to the x. Now I'm at least closer to seeing if this is going to be 0 over 0 or infinity over infinity. Is this going to look like the right thing? Well, what is the limit as x goes to infinity of x squared? What is the limit as x goes to infinity of e to the x? Both those limits, right? X squared is the parabola, e to the x is my x, they both go off to infinity. Wonderful, marvelous, wonderful. This is exactly the indeterminate form I'm looking for. So I'm going to do L'Hopital's rule. That little LH over the equal sign is what reminds me, hey, I'm doing L'Hopital's rule here. What is the derivative of x squared? And the derivative of e to the x? Well, I still have something on top, something on bottom, and I know the bottom is an infinity. What's the limit as x goes to infinity of 2x? Ah, damn it. It's still infinity over infinity. If it's still infinity over infinity, I still use L'Hopital's rule. Do it again. Well, now I am absolutely sure I am done doing L'Hopital's rule. What's the derivative of 2x? That is definitely not going to go to infinity. That is definitely not going to go to zero. That is 2 no matter what the hell else I do. What is the derivative of e to the x? And that's going to go to 2 over infinity. And 2 over something huge is teeny weeny. That means this goes to 0. So I had to manipulate my expression first to get it into a quotient, check if I could use L'Hopital's rule, and then use it until I ran out of infinities or zeros. What this tells me is that as x gets bigger and bigger and bigger, the 0 that is the e to the negative infinity is stronger than the infinity that is x squared. Because I'm multiplying those two together, and here in this case, the 0 wins. Big O of e to the x is bigger than big O of x squared.
What are you?
Like as soon as class ends. Oh, that's exactly what. I get through today, the homework keys and the review sheet key will go up as soon as class is over. They're all sitting on our Canvas page, just waiting for me to click publish. More questions? Uh-oh, how did it break? Go back. Why? Yeah. There you go. Somehow something you were doing was statistically related, because that's a statistics plot function. And that if you don't have anything entered in the list, it reads that as a dimension error. You're trying to plot an empty list. I don't know how to do that. There is also a plots off button. So if any of those ever get highlighted, you can hit above y equals, it says stat plot. If you hit second stat plot, there's a plots off option. It turns all of them off, but you'll be able to see if any of them are on. See how it lit up? Now, if I go back, it shows that one as being on. But I can also just hit this plots off and they're all off again. That's for doing all sorts of interesting things in the stats class. If you haven't taken stats yet, you should. I don't know why I turned on. Some of the programs that run in the background of some of the games I've seen programmed on calculators, which always was bizarre to me. Why would you put a game on a calculator? I saw somebody put Snake. You remember the Snake game on their graphing calculator? Weird stuff. But if that's what happens, that it plots things. So turn off the plots. That always helps. Until you have stats class where you'll need them. More questions? Well then, ladies and gentlemen, I will see you all on Wednesday in the afternoon. If you have questions, please come see me in office hours. Hope you have a wonderful rest of your day and a good exam week. As far as I know, yes, the review session for the exam is tonight. Hang on, I can check my calendar, just in general. Calendar. Yes, I've got it as, what does that say? 7:30 to 8:45 tonight? Thank you.